A green revolution in gold, light, salt, and science replace mercury and cyanide. Gold mining has long come at a high environmental cost. Toxic chemicals like mercury and cyanide have been essential to traditional extraction methods, posing serious risks to human health and the planet. But a groundbreaking development from researchers at Flinders University could dramatically change that. By using only light, salt, and a recyclable polymer, scientists have discovered a clean, efficient, and scalable way to extract gold, not just from ore, but from one of the world's most alarming waste problems, electronic waste. This innovation is more than just a lab success, it's a viable solution tested on circuit boards, mixed metal ores, and even scientific waste. The technique was developed by an interdisciplinary team of chemists, engineers, and physicists, all working together toward a single goal, to design a gold extraction process that avoids the use of mercury and cyanide entirely. Their findings, published in Nature Sustainability, demonstrate that it's possible to recover high-purity gold using safe, low-cost materials while also creating a circular, reusable process. At the heart of this process is a compound called trichloroisocyanuric acid. Commonly used in water sanitation, like pool disinfectants, it serves as a leaching agent. When combined with salt water, it can dissolve gold from materials that contain even trace amounts. Once dissolved, the gold is captured using a sulfur-rich polymer, which binds to the gold with high selectivity. The beauty of this method lies not just in its simplicity, but in its sustainability. The polymer can later be triggered to break down, releasing the gold and regenerating itself for reuse. Led by Professor Justin Chalker at Flinders University's College of Science and Engineering, the research team tested the method on a wide range of sources, including discarded computers and mining ore concentrates. The results were impressive. The team successfully recovered gold from various complex waste streams, proving that the method is both versatile and effective. Their goal is now to scale this process and work with mining and e-waste recycling operations to deploy it in the real world. And the urgency could not be greater. As of 2022, the world generated an estimated 62 million tons of e-waste, yet only 22.3% of it was formally collected and recycled. Much of this waste is hazardous, containing toxic materials that pose significant threats to human health, substances like lead, mercury, and dioxins. Poorly managed recycling practices only make things worse, especially in low-income regions where safety regulations are often lacking. The stakes are just as high in the mining sector. Artisanal and small-scale gold mining operations continue to rely on mercury to amalgamate gold from ore. This practice, which involves evaporating mercury to isolate gold, releases dangerous vapors into the air. Studies show that up to one-third of miners in these operations suffer from mercury vapor intoxication. Globally, between 10 million and 20 million people, many of them women and children, work in these informal mines across more than 70 countries. These operations account for about 37% of global mercury pollution, releasing an estimated 838 tons each year. Despite the danger and environmental cost, these miners often operate with limited resources, without access to safer alternatives. They represent roughly 20% of the world's gold production, generating around $30 billion annually. But due to lack of regulation and exploitative conditions, they often sell their gold at prices far below global market value. Many are trapped in cycles of poverty, burdened by predatory loans and unsafe working conditions. This is where the Flinders breakthrough could have its most profound impact. The new method offers a realistic, low-cost pathway for transitioning to mercury-free gold recovery. It's safe, scalable, and doesn't rely on dangerous chemicals. In trials conducted with collaborators in the United States and Peru, the method performed well even on traditional mining ore. That means it could be adopted by artisanal mining communities, reducing their reliance on hazardous substances while increasing their yields and safety. The technique also stands out for its green credentials. The polymer sorbent is made through a UV light-triggered reaction, allowing the researchers to manufacture it in an energy-efficient way. After the gold is captured, the polymer can be broken down back into monomers and reused, making the system inherently circular. According to ArcDecra fellow Dr. Thomas Nichols, this closed-loop design adds another layer of sustainability to the already low-toxicity approach. Dr. Max Mann, one of the lead postdoctoral researchers, emphasized the collaborative spirit behind the work, noting how tackling e-waste and resource recovery at this scale demands interdisciplinary solutions. The team's hands-on approach even led them to recover gold from real-world piles of discarded electronics, including CPU units and RAM cards. These components contain small but valuable amounts of gold and copper, often discarded as trash. Dr. Harshal Patel described the moment vividly: "We dived into a mound of e-waste and climbed out with a block of gold." It's more than just a metaphor. It represents a future where science helps turn today's waste into tomorrow's resources, without compromising environmental safety. Dr. Lynn Lisboa reinforced the broader significance. With rising global demand for gold across electronics, medicine, aerospace, and finance, the pressure on traditional mining will only intensify. Developing cleaner, safer methods for gold recovery isn't just important, it's essential. Beyond the technical innovation, this project reflects a shift in how scientists view their role in tackling global problems. Professor Chalker highlighted the importance of working with philanthropic, industrial, and environmental groups to bring these technologies beyond the lab. The hope is to create viable economic pathways for communities, while protecting the air, water, and ecosystems that mining activities so often damage. This work is more than just a technological breakthrough. It is a blueprint for rethinking how we value waste, how we protect people and the planet, and how interdisciplinary science can offer real solutions to real problems. With the support of global partnerships and a growing awareness of the environmental toll of gold production, this cleaner method could help rewrite the future of resource recovery. In a world increasingly defined by scarcity and environmental urgency, the ability to recover gold with light and salt, safely, affordably, and cleanly, might just be one of the most important discoveries of the decade.